All right, this is number 15 from section 7.4, where we want to use partial fraction decomposition. Now, partial fraction decomposition sometimes requires a preliminary step where we want to get the degree in the numerator less than the degree in the denominator. Often that would involve a polynomial long division, and we could do that here. That's the setup where you would imagine having x cubed minus 2x squared minus 4 on the inside and x cubed minus 2x squared on the outside. And if we were to follow that method, we ask how many x cubes go into that first term and write along. If we did that, we would end up with an answer that we could have gotten another way for this particular problem. So for this particular problem, I'm going to note that the first two terms there match completely. And so if I were to split this up, I could imagine doing it like this, where I have x cubed minus 2x squared and x cubed minus 2x squared here, minus 4 over x cubed minus 2x squared. But that first term is just equal to 1. And this is the result we would have gotten from polynomial long division. All right, now we're in a place where we can do our partial fraction decomp. To do that, I really like to do this as side work, so let's just do that. I'm on a computer. I'm going to go to a different page. So we're going to take this 4 over x cubed minus 2x squared, 4 over x cubed minus 2x squared, and think about how we can decompose this. So in the denominator, we have an x squared times x minus 2. So this is going to give me, with partial fraction decomp, this guess. With the x squared, it's a repeated root, so it'll be a over x plus b over x squared. And then x minus 2 is a linear, non-repeated root, so it's just c over x minus 2. Now I'm going to imagine putting these back together into one fraction that would have the same denominator that we had before. And think, what does each term need? So the a, to get back to that fraction, needs an x times an x minus 2. The b, to get to that denominator, would require just the x minus 2. And the c would require an x squared. So now let's think about this. On the left-hand side of this equation, we have just a 4 in the numerator. So if I were to track each of my terms, I'm going to say, well, my biggest term is going to be an x squared, or the highest degree of x. And so how many x squareds do I have on the left-hand side? There's none of them. On the right-hand side, I'm going to get an x squared out of the a. There's a single x squared that would come out of that one. So a times x squared. And then I have the c times x squared. So there's ax squareds from here and c from the next. For the x terms, where do I get those? Well, I have minus 2 times ax. I have b times x. I'm trying to change the colors here. Plus b and no c. And then there are 0 x's on the left-hand side. And then finally we have, for the constant terms, 4 and just minus 2b are our constant terms. So this gives me these numbers that b is negative 2. If that's the case, a would have to be, from this next equation up, negative 1 to make that work, and then c would have to be positive 1. So then our answer would be, for this partial fraction decomp, I could write that as negative 1 over negative 1 over x, excuse me, from right here, plus, or let's say minus 2 over x squared for the b, plus 1 over x minus 2. Great, so that's what I'm going to take to solve over here. So let's go back to our other page here and say this equation, where did it show up? It's over here. Here we go. Gonna shrink that down a little bit if it lets me, and if it doesn't, that's okay. This is our last term there. And notice we had a minus here, so I'm gonna go ahead and change these signs here to the negative version. And then we have 1 plus all that. Okay, great. With the dx. So there's our partial fraction decomp. And now we just go through it and integrate. And it should be from 3 to 4. So first, let's take the integral. 1 goes to x. 1 over x goes to natural log of x. 2 over x squared goes to, we should make that negative, negative 2x to the minus 1. And goes minus the natural log of x minus 2. And we're going to plug into that 4 and 3. When we plug in the 4, we're going to have 4 plus natural log of 4 minus 2 over 4, so it'll be minus a half, minus natural log of 2. And then when we plug in the 3, it'd be subtract off this whole thing, 3 plus natural log of 3 minus 2/3 minus natural log of 1. And I could simplify that more, but I don't want to right now. There you go. All right, this is problem 30 from the section 7.4. We have the degree on the denominator is larger than the degree in the numerator, so we are ready to do partial fraction decomp. What we need to do is factor the denominator first. So even though we're going to take an integral, I think it's helpful to start out by just thinking about the partial fraction decomp. So let's ignore the integral for the moment. Let's factor the denominator here. Right. So the denominator could be factored into this form. We need to thinking about this even powers. And so this is kind of like you have the number x squared plus 1 times x squared plus 2. Right? The 1 and the 2 multiply into 2, add into 3. Instead of having an x and an x squared, we have an x squared and an x to the 4th. And now the numerator stays the same. So here's the trick. X squared plus 2, does this factor? X squared plus 1, does that factor? Well, if it factors in the real numbers, here's what I think about. If it factors in the real numbers, then it intersects the x-axis somewhere. These two problems clearly are parabolas facing up that have been shifted up, right? So there are no real factors to this problem. You could also think about, if I'm trying to factor this x squared things, I could think about the quadratic formula, which has that negative b plus or minus the square root of b squared minus 4ac. And think about what's under that sign right there. If the b is 0 and a and c are positive, then this would be negative 4 times a positive number. So this would be an imaginary number. So the roots of this are not real numbers, but imaginary numbers. And so that tells you they're not factorable anymore. So we're going to do this. We're going to use those as part of our guesses. So using partial fraction decomp, the good guess for this would be, with the first term x squared plus 1, since it's not reducible, our guess on top with the a and the b will be ax plus b, 1 degree less. And we'll need that in order to have a sufficiently good guess for all the solutions. And then the other one is x squared plus 2. And on top is c plus d, cx plus d. Very good. So now, following our typical partial fraction decomp strategy, we're going to put them back together in a single fraction. And what's going to happen is we're going to have an ax times the x squared plus 1, or plus 2, excusez-moi. And we're going to have a b times the x squared plus 2. My gosh, I'm writing much too large. Let's zoom this out a little bit. Following that, we're going to have the cx times x squared plus 1. And we're going to have the d. We are going to have the d times x squared plus 1 as well. And all that will be over the original denominator of x squared plus 1 times x squared plus 2. Now is a great part where we're going to match up. Looking at the numerator here, our highest degree will in fact be an x cubed, which is even a little bit higher than we had over there in that numerator, but that's fine because we're going to get some zeros. So we're thinking about the x cubed terms. Where are those going to come out? Well, x cubed will show up here and here. So the x cubed terms on the right-hand side is just a times x cubed and c times x cubed. And on the left-hand side, that is in the numerator of the original problem, there are 0 x cubed terms. Follow that along. We've got 3x squareds. We've got just a b and a d. Do your x terms. We have 1x. We've got 2a. And we have c. And then following our constant terms, we have a 4, a 2b, and a d. Okay, so this is the thing that we have to solve. You could decide where you want to do that. You could either use a matrix here, or you could do it the old-fashioned way. Since it's pretty nice, let's think about these two terms here. If I subtract the blue from the red, I'd have 1 minus 0 is 1, equals 2a minus a is a, c minus c is gone. So a is equal to 1. And likewise, c would have to be the opposite so that they add to 0. We could do the same thing with these two terms here. If I did 4 minus 3, I have 1. 2b minus b is b, and d minus d is 0. And so if b is 1, d would need to be 2. So those are our terms. So to stick those into our equation, remember looking at it right here, I'm going to keep smaller and smaller, kids. That means our fraction decomposed would be a is 1, so x plus 1, b is 1, over x squared plus 1, plus c is negative 1, so negative x plus 2 over x squared plus 2. Okay, so here are our terms, and we want to integrate this. So here we go. So we're going to take an integral of this. Now, this could be a place where it's helpful to follow some of those examples in your books where you had a term in the denominator that was not reducible. Because a couple of things can come out of it. Just looking at time, we have about a minute. I would do this in 4 different fractions. So I would do the integral of x over x squared plus 1, because that will be different than 1 over x squared plus 1, dx coming along for the ride for each of these, minus x over x squared plus 2, dx, plus 2 over x squared plus 2, dx. Because the ones that have the constant on top will end up with an inverse tangent, and the ones that have an x on top are going to end up with some sort of logarithm. I'm running out of room here on the bottom, and so let's just sort of recognize what these would be. For this term right here, you would end up with, if I let u be x squared plus 1, it would fall out that when I integrate this, I'd have 1/2 the natural log of x squared plus 1. Next, 1 over x squared plus 1, that is just inverse tangent of x, minus, this one's very similar to the first one, because the 2 and the 1 don't really change much as insofar as the chain rule is applied. So we would have 1/2 natural log of x squared plus 2. And now when you have the 2 here, things do get a little bit more funky. So if we look at the back of the book, we'll see this answer, plus a constant.